So we make this move somehow in one way or the other. So they can move in this direction, then we can write down this equation. So this gap, this initial gap E, gets modulated now by the displacement x. And how I choose the coordinate system, how I choose the direction of this x is up to you. Right? It doesn't matter. So if I choose this x to point in the other direction, I would have to change here the sign. So that is just it's an arbitrary assumption. It's like when you do circuit analysis and you do Kirchhoff's nodal analysis. The direction of the current you can assume whatever direction. Okay. So okay, let's look at this here a little bit. So the C of x. Yeah. Well, first of all, what we can say is C varies with this displacement x in a nonlinear y. We have a nonlinear relationship. It's some sort of 1 over x relationship. Okay, so we have a nonlinear change in capacitance with the plate displacement. Now, nonlinearity, is this a problem or not? Well, I would tend to say it's not a big problem. Why? Because if we know the relationship, right? We do know by this equation. We know there's a relationship. I can use some computer power, some digital signal processing to linearize it. I can easily linearize this if I know the relationship. So I can work with this nonlinearity in the electrical domain. I can compensate with this for this nonlinearity because I know it. Then I can deal with it. So it's okay. Nonlinearity is also nice, but okay, I can deal with it. So that's one point to make. Another point to make is, of course, this x here, this displacement, is limited. It's limited by the initial gap d here. I cannot make this x here larger than the initial displacement because it will bump into this lower entropy. And that's something already which is not so easy to deal with. Usually this is not to scale. Usually this d is small compared to the side length. Otherwise you get these parasitics I was talking about before. So usually this distance d here initially, the initial distance d is already rather small. Typically in the order of a few micrometers. Okay. So that means that this plate here only can move at most a few micrometers. Actually, it should not move more than, for another reason, I'll get back. I'll get to next week. It shouldn't move more than actually 30% of the initial gap. So take this as a rule of thumb for the moment. Explanation to follow. Why? Okay. So anyway, so we have a clear limitation on how far this electrode here can move. All right. And because we have a limitation here, we may have a problem with the dynamic range of a sensor. Because the dynamic range is somehow determining how far this this plate here can move. If I have more pressure, then at some point this will go down until it touches it in the limit. And okay, there are ways of doing this. You can use some sort of feedback to increase the dynamic range. So some feedback that somehow pulls this up again in the presence of some sort of quantity that deforms your pressure. Right? So this is a closed loop feedback MEMS sensor. So again, hopefully I have time maybe in the last lecture to explain that a bit more. Okay. And now a last point is, what's the sensitivity? So the displacement is actually what we want. That allows us to measure, we stay with pressure here, okay? So the more displacement I have, the more sensitive my device will be, the more changing capacitance I will get. Now this is a contradiction to what I just said, because with this dynamic range argument here, I said the X should be small, and now I'm saying the X should be big. And indeed, that's always a design trade-off. There's always a trade-off between sensitivity, dynamic range, and often the bandwidth of the sensor as well. And yeah, this is sort of the old story. There's no free lunch. You make one quantity big and the other one goes smaller. So how can I define or calculate the sensitivity? Well, I can calculate the sensitivity to take if I take this C of X and I differentiate it with respect to X. Right? So I can calculate dC dx very easily, and then I get this quantity there. So that's dC dx. Sometimes I should maybe write down. This is also written down as so if I write this dC dx. So look, if you look at this equation there, I've got the original C of x in there. So this is my C of x divided by d minus x. Epsilon a. Oh, no, it's in there. So this C of x, epsilon a, d minus x. Well, if I write this as C of x, I only get d minus x. So you see also this in the literature. Now, the sensitivity, of course, of a sensor should be high. I want to have so much sensitivity as I could get. That's one of the figure of Marius for any type of sensor. And what does this indicate? Well, I should make the gap d minus x squared. I should make this small. So for smaller gaps, it goes even with the power of 2. For smaller gaps, I get a higher sensitivity. So that's a guideline as well. The higher the sensitivity you want, the smaller that you should make the gap here. But you might have a problem with the dynamic range, because then the displacement gets really small, what you can see. Okay, now I could do something else. So here I have what's called a gap closing capacitive sensor. So I'm closing the gap. The two electrodes are moving towards each other. But I could also do this here. I could also say, okay, I leave the gap D, I leave that constant. And I make a construction, a mechanical construction, so that my one electrode can only move in this direction, in the x direction. So x is defined now horizontally. Okay. So this is a lateral plate motion, or a lateral plate capacitor. And I can write down now again my equation for my approximate equation for the capacitance, which is that. So I take the parallel plate approximation again. So now I have L, and L varies now. It's overlap L with this electrode. This varies by x. It's being modulated by x, and I have some sort of W. And W, if I turn this upside down, I can make this. And a W is then what comes out of the bore. It's the depth or the width. Or here would be what also comes out to its U. Let me go back again. So that's W. So W times L minus X, that gives you the overlap area. And then divided by D, that's the distance of the electrodes. And this D here is now constant. Okay. And I of course have to make a mechanical construction somehow that this is the case. So this D has to be always exactly constant. So that's the suspension system somehow. Okay. So how this is being constructed, I'll show you a bit later. So so then we have this equation, and I do the same calculation. I can calculate the dc over dx for the sensitivity. So I do the derivative, and I get this here. And if you look at these parameters, this is constant. So this is independent of x. It's constant. So that's a clear advantage. You don't have a non-linearity here anymore. So if I go back, here I have this 1 over x relationship of c of x. Sensitivity is over x squared even. So sensitivity is dependent on the displacement. It changes. Both quantities, sensitivity as well as c of x, change in a non-linear way. But I also did say that this is not a big deal. And I also did say already on the board last week, if I take 2 of these capacitors, so here we are talking about 1, but if I have an arrangement of, like, I make 2 of these capacitors, and this is my x, and I measure the differential change in capacitance, right? Then we also got a almost linear relationship, right? I had to make an approximation that my x was small in comparison to the initial gap, but it's a fairly good approximation, right? So here it's different. So this is a single-ended capacitor. This is a differential capacitor. But nevertheless, if I do this, this lateral plate motion, then I get a linear relationship of C with X. So C is somehow proportional to X. And my derivative is a constant. So it's not dependent on how much displacement I have. Okay. However, to a constant sensitivity, right? However, if you look at now, if you take typical numbers, so this is something you can do in your own time, for W and D, and you take, again, typical numbers for W and T, well, the same numbers, you calculate this sensitivity, and you calculate that sensitivity, for, okay, it depends on X, but you make an assumption about X, let's say it's 10% of the initial gap or something like that. If you do the calculation, then this figure here will come out about a factor of 10 larger than that figure. Right? So that means this gap closing capacitance is more sensitive to a displacement than this lateral plate capacitance. And the rule of thumb is a factor of just under 10. So this is linear, but it's less sensitive. So it's again same story as always in life, no free lunch. Okay? Right. Now, this here is an arrangement that is rather simple. And what I can do, I can do something like this here. Right? So this is a comb finger structure. And of course I can extend this to not only 2 fingers, right? I can also extend this now to many more. I can copy and paste this in that direction, right? And then I form that, right? So I do this. Okay. Why do I do this? Well, because I make the C bigger. Right? So each of this method here, or this concept here, applies to any of these finger gaps here. Right? So I can multiply this here by, well, in this case, a factor of, well, actually it's a factor of 4 if you think about it, because I have a capacitance between the white and the top yellow, and between the white and the top bottom. And here again, so I would have to multiply this by 4, and if I copy and paste this, I can multiply this by n. So it's a trade-off on how much fingers I have. And that's a trade-off, of course, how much silicon area I want to allocate to this sensing principle. Okay? Yeah.
Well, we said that for the parallel plate capacitance, this equation is pretty much accurate.
This here?
Yes.
Well, it's again, it's the parallel plate approximation.
But in the lateral plate, how can this relation still be?
It's the same. It's the same problem.
Because it's shifting the 2 plates, it should make the situation even worse. Like the
field. So if you take this here, so like this. So what I calculate is making an assumption about a homogeneous uniform electric field like that. Right? And in fact what I have is also that. Okay? And probably here as well. Yeah? Right? Now this part here, so basically what I have here is that part is my C parallel. These are the equations here, parallel plate approximation. But really what I have there is a C parasitic, right? And often, not always, but often in MEMS designs, this is for in the order of maybe 20%. That is a very, again, rule of thumb figure what I'm giving here. It can be 100, it can be 1%. It really depends on the design. But 20%, if you have to guess, then 20%. That's a good figure. Now, if this shifts here, so if I move this now by x, right? Then I have this equation there, and it changes the C parallel, but it does not change first order approximation, the parasitic here. Because whether this edge here is at that point or a little bit further, these field lines here remain more or less the same. Right? Now, again, this is also an approximation. If you now go to this here, you can argue, well, the feed lines between there, the front end, and the yellow area there, they do change if this moves sort of in and out. So again, it's an approximation. But to a first approximation, you can say the parasitic capacitance usually don't change with displacement, whereas the parallel plate capacitance, they do change with the displacement. Right?
So the thing is, even though we have maybe more parasitics here with respect to the other case, we can say probably, but
Yeah, I'm not sure whether you can generalize that you have more parasitics. Yeah? In the other case, yeah, yeah, I have field lines like this, right? And so on and so on. Yeah? Are they more or are they less? Depends now really on the accurate geometry of your design. Yeah? I would not say that in general you would have more parasitics in the lateral compared to the parallel plate case. Yeah. Okay? Yeah. So, sensitivity, cold finger design, yeah. Sometimes it's also called an interdigitated finger design. Yeah. Okay, now this is, yeah, I said we have to create suspension systems that either limit the motion in this direction, lateral or perpendicular. So in reality, this is also a some sort of approximation. Yeah? Why? Well, okay, let's go back to our pressure sensor. Yeah? So here I have two plates, and there's a medium here in the middle. You can say this medium is a dielectric, or you can say it's air as well. You know, that's also important, but it's not a solid. Huh? So parallel plate approximation again gives you this, and now what I do here is I put a force here in the middle, yeah, and this deflects, and now you get sort of a bend shape of your electrode. Yeah. So before I make the assumption that one electrode is really moving nice and parallel with respect to the other one. And here, what I'm making an assumption now is that this membrane is bending down like a bit like a trampoline. Yeah? Okay. Now, does that matter? Well, it makes the calculation more difficult of how much change in capacitance I get. Why? I have to solve some sort of double integral. And this W here, it's indicated there, is a function of x and y. Right? Okay, so I have to do a double integral calculation for C of, now I shouldn't be calling it x anymore, it's a C of x and y, yeah, or a C of W in this case. Yeah? But I have to integrate over the area of my membrane here. Yeah, this can be a round membrane, then you have to do some sort of spherical coordinate integration, or it can be a square membrane, yeah, and then it's normal Cartesian coordinate integration. But okay, this can be solved. Yeah? You spend a Sunday afternoon on this and then you solve it. Yeah? Not so dramatic. It's a non-linear relationship again, and yeah, non-linearity, I said, as long as we know what it is, we can deal with it. In the electronic domain, you effectively use MATLAB and you do one over this, and then poof, non-linearity is gone. And this is, of course, what you can do in electronics more or less as well. So, we are back, as you see, to pressure sensors, because this could be the membrane of a pressure sensor. And here is a real curve here, so this is some sort of medical pressure sensor where we look at pressure in millimeter mercury. Yeah? The unit they use for blood pressure measurement, and this is the sensitivity. So yeah, it's a non-linear curve. Yeah. But it has a pretty linear part here, and I know the non-linearity because I can solve this, and so I can deal with this. So whether it's a membrane or a nice parallel plate motion, where the electrodes remain parallel, well, okay, we can deal with it. Huh? So, how can we make now an actual pressure sensor, a capacitive pressure sensor? Huh? Before we had talked about a piezo resistive pressure sensor. So, it's shown here. So I'm still doing bulk micromachining, sort of KOH etching of a cavity. I stop here at a certain distance of the, or certain thickness of the membrane, defined by boron implantation or electrochemical etch stop or so. And what I do then, I bond here a glass wafer, particular type of glass, Pyrex. This is Pyrex wafer. On top. Now, if I have to have a capacitor to be formed there, if I want to have a capacitor, I need two electrodes which are two conducting areas. So I need to have made here, first of all, I have to also etch my glass. And I have to put here a metal. So this metal forms the one electrode. And this doesn't move. This one here is a big glass wafer, very stiff, doesn't move. And here I have my thin membrane. If I have a pressure here, it will deflect. So I have the first case, the two capacitive plates or cases. So this is aluminium here, which is sputtered. Now one of the problems here is somehow I need to have electrical contact to this electrode. So I have to get an electrical contact out to the outside world from here. And I bonded this, so I'm noting bonding, yeah, okay, I can bond if I have a thin layer of metal here. And the way this is being done here for the electrical contact is that I have here an area of high P plus silicon. So here has been some sort of implantation step done to make it a very high P diffusion. So this is a line, rectangular strip, and that then goes to a bond pad, which is a metal deposit. And here I can put a bond wire. So in this wire, it makes electric contact through here to this electrode. And the other electrode, well, this is silicon, and this maybe is N-type doped silicon. So I don't have a short, I have a PN junction to isolate the two things, the two electrodes, and I can here have another, maybe a metal contact there or here to contact the other electrode. Okay, so now I'm done. So I've got my pressure sensor, and then I can start measuring. Right, I can now do this. So here is my capacitance, should be not capacity, my C, as a function of pressure, and that increases with pressure. Why does it increase? Well, because the capacitance becomes smaller with pressure. So the electrode distance becomes smaller. And at some point, so this is the upside down of that. Conceptually, at some point, I will have the case that my membrane touches the bottom. And then some other nonlinear stuff will happen. Yeah? Actually, now whether this is a disaster or not depends on your design again, on these particularities of your device. Yeah? It can be like here. Actually, it makes it nice and linear, huh? Because you kind of start rolling. This front here starts rolling or spreading out in all directions. Huh? So if I measure the capacitance here further, then suddenly there's, from the point on where the membrane touches the bottom, becomes a linear relationship. Yeah.
What is the definition of the capacitance in this case? I mean, they are single metal now. They are short circuit.
Yeah, well, that's the point. It depends on the actual design details of your device, whether this is a disaster or not. And you're right, the way I've explained it so far, you would actually create here an electrical short between the bottom and the top electrode. Now, what can you do is, for example, you put here a thin silicon dioxide layer. And then the silicon dioxide prevents it from making an electrical short. It's actually a dielectric. So if you do that, then this is not a disaster. Okay? So it depends really on the details of the design. Yeah.
You don't have a method like on the bottom layer of the capacitor?
No, I make the assumption that this is a reasonably good conducting silicon. So it's doped silicon, probably n-doped silicon. It doesn't say here, but it's n-doped silicon because this is P plus. So you have to have some PN junction so that you don't get a short circuit again between the two electrodes. If this is a medium doped N-type silicon, then it's conducting enough to form the electrode of a capacitor. So you can use the silicon directly. Now, how well it has to be doped, that has to do with the fact of how fast do I have to charge and discharge somehow this capacitance. So there's a link to the bandwidth because, you know, doped silicon, if I create a sort of a lump model, electrical equivalent lump model from it, I can say, well, it's a capacitor and it's a resistor. And how much the resistance is, that I can control with the doping. Right? So I have an RC, and RC has a time constant, and then we add bandwidth. Now for pressure sensors, this is usually not critical because pressure sensors are, pressure doesn't change so fast usually. There are exceptions. We just had a discussion with people from the Kalman Institute. They want to do pressure changes up to 10 kilohertz, maybe 100 kilohertz even. And they're interested in having measuring pressure changes inside the turbine of an airplane. And there suddenly you are getting to frequencies where you have to think about these effects. If you want to measure barometric, so the air pressure, doesn't matter. So again, it always depends on the details. The devil's always in the details. Yeah. Okay. Where was I? Ah, yeah. Here. Yeah. So okay. So this, whether this is a disaster or not, depends on the actual design. Of course, you cannot form a electrical short, so then it's game over. That mustn't happen. What you can also do is play tricks like that. Yeah? So I can work in the mechanical domain to reduce this nonlinearity. And if I do this here, right, you can sort of, well, I think you can intuitively imagine that the electrode here will move up and down in a more parallel plate way, yeah? Remains more parallel for small deflections of course and so on. Yeah, okay, so this is something that has been proposed, so I don't think it's too important. But you can play tricks like that, yeah? You can improve this 1/d relationship in the mechanical domain. Right. Okay, so let's look at a few more real devices. So this is the cutaway view. So here the glass is at the bottom. Here is this gap, quite small. Yeah, different diagrams, cross-sectional and top view. And here's the actual device. Okay. So that's a capacitive actual pressure sensor. Here a few more pictures. The glass has the nice property that I can see through. Of course, so I can see what's sort of going on here. Apart, of course, where the glass has been covered by the aluminium electrode. So this is the metal. So this is and here's the contact track. So this is cavity. Bore implantation for the feed through here. Right, and here's another. This is the connector to the silicon electrode. So this would be a connector somewhere to the silicon structure. Right. Okay. Now here's another. Oh yeah, sorry. So that's the pressure sensor. Now, just to give you a glimpse of what is to come. I can use the same technology effectively. I slightly change the construction. So I have here my glass with the fixed electrode that's bonded here. So this is an how's this called? An explosive view, exploded view of it. I'm sorry. This is glued together, so to say, in the real assembly. But the middle thing here looks different. Huh? So this middle thing here is not a thin membrane, but it's a rather chunky mass in comparison to this thin membrane on what I had before. And so this is big, 1.8 cubed millimeter. So this is a seismic or a proof mass. And a mass reacts to acceleration. So I have my mass, and you take Newton's second law, and the mass times acceleration gives me a force. And this force acts on my mass here, and if the force, or if the acceleration is actually acting along this axis here, right, then it will try to deflect this proof mass. Now this proof mass is here suspended by a thin beam, and there are no gaps here. So gaps to the left and right. It's not floating in mid-air. So this will go up and down. We'll change here the capacitance, right? According to this force, and so I measure this capacitance becomes a function of this force, right? And this force is a function of the acceleration. So this capacitance here gives me some sort of non-linear, but it gives me a measure of how much acceleration I actually is acting on my proof mass. But what I built here with very similar technology is an accelerometer. Okay. And then there's another sealing plate on the other side, but maybe you don't need that. Okay. So this construction or this technology is not only suitable to pressure sensors. So that's the main message. We come to accelerometers in a bit more detail in the next weeks. Now, one other aspect of capacitive sensing, again more general. There's a question here. Go on.
Yeah, sorry. Could you please explain what you see? Like what component is what?
What is it you don't?
I mean, I don't understand what is the glass and what is the silicone.
This is the glass.
No, in the optical image.
Ah, here.
Yes.
What you see here, this is the electrode. So this is the metal. So you see through the glass. The glass you don't see because you see through it, and you look onto the onto that.
So I see from the top.
Yes, yes. And then you have this track here, right, which is sort of indicated by this is a bad drawing in a way. Yeah? So this is the this is indicating this track that allows you to make contact to the electrode, right? And this here is the silicon. Okay.
Yes, thank you.
Yeah. Okay. So one more more general point about capacitive sensors. So I sort of hinted already last week that they are having a lot of advantages in terms of sensitivity, and you can measure amazingly small deflections, right? But they have also disadvantages. And one of them is sort of indicated here. So here you have a blown up view of this pressure sensor again. Yeah? So you have here the membrane, you have here your capacitance. Here actually you do have a thin layer of silicon dioxide. Yeah? So this is there to prevent what one of you guys over there said. If the electrodes touch, you mustn't have an electrical short. So here you have your thin silicon dielectric, or silicon dioxide as a diode to prevent this short cutting. And this is your capacitance. So that's what is changing between the electrode there and the electrode there, which is actually the, okay, so the thick black lines are the capacitor plates, right? And the capacitance you're working with, what you want to have, that is changing, that's actually not shown here in the diagram. What is shown here are parasitic capacitors. and there are quite a few. So for example, between here and the thin dielectric, you form, of course, a parasitic capacitance. And you also form a parasitic junction capacitance if this layer there is, let's say, N-type, and this here is P-type. It's a junction capacitance, all the other way around. Doesn't matter. Okay, so the different colors here indicate that this is a different doped silicon to that. Why? Because electrochemical edge stop, remember? We needed that to create a thin membrane. This is again not to scale. I should always have to say this. All these diagrams are not to scale. So we needed this for the electrochemical edge stop to create here a thin but well-defined thickness membrane. So we have a different silicon doped layer here to there, therefore we have a junction capacitance. And the same argument now you can make with resistors. I touched on this already. Okay, so resistance is not so important, but you have a lot of parasitic capacitance, and usually they tend to be so that they don't help. So they short, or they shunt, I should say, they shunt some of your signal to somewhere you don't want it. So they reduce your signal. And so this was one effect here, okay, where you have CPs, fringe fields. That's another effect. Yeah? So you have also other parasitic capacitance. And that's a very general point, a very general problem for capacitive sensors. Parasitics are always present, and they always reduce your signal. And how exactly and how much these parasitics are, that is depending on your design again, on really the details of your design. In general, you try to minimize those. Okay. Now, about some of these parasitic capacitances, I can do something about, right? So, for example, if I have parasitic capacitances and I have electrical connection, or the possibility to electrically connect both sides of the capacitor, then I can just simply electrically short them, right? Or ground them. So if I ground both sides of the parasitic capacitance, hey, then I don't care. So that's one technique. So you try to form actually some sort of Faraday cages around your working capacitor. So for example, if I have electrically access to here, to this node and that node, then I can ground this. So that means I need to have access to the substrate, to here. So that's one strategy to deal with parasitic capacitors. Another problem with capacitive sensing, not shown on this slide, I'll just tell you about it, is if you have electromagnetic fields, stray fields, which of course are everywhere around us, from electrical equipment, or from, if you think of a car, in the engine you have a fuel type engine, you have a ignition coil. So they send out, when they fire, a very sharp electromagnetic wave. An electromagnetic wave they tend to couple into capacitors, because these metal tracks and connections and so on, they're always antennas as well. So electromagnetic stray fields, strong stray fields, they can disturb your capacitive sensor. That's one problem in general. So electromagnetic stray fields are an issue with capacitive sensors in general. Okay, yeah, here's a real device again shown, real design. It also gives you some numbers. So the gap here is 1 micrometer. The membrane thickness 10 micrometers. And here you see the outer dimensions. This is also all in micrometers. So the membrane itself was 1 by 1 millimeter. So if you have now dimensions like this, this is 1,000 micrometers. The gap here is 1 micrometer. You don't have to care much about stray effects. So the parallel plate approximation is a very good one in this particular design. You also may notice you have actually here 3 contact paths, 3 bond paths. One for the bottom, one from the top electrode, AV. So this is your CX, your working capacitor. That's what's supposed to change. And then you have another one here that is allowing you access to the substrate. And why? Well, because you want to put this on a defined potential. You want to ground this well. That deals, or at least addresses to some extent these parasitic elements you have. Yeah, notice the third electrode. So this is the ground connection to the for the substrate. If you look at this device here, this sensor, well, it's pretty small. 3.5 mil times 2.5 mil, and the thickness 800 micrometers. Yeah.
Does the membrane thickness define the range in which the capacitor acts as the resistance?
Yes, it defines the dynamic range. Yes. If you wanted to now to measure a higher pressure, right, then you would have to make this the thickness here a little bit thicker. You make it stiffer, at the expense of sensitivity. You get less changing capacitance and less signal there. Yeah. Okay, so this is pretty small already. Yeah. If you want to make it even smaller, you could do this. So what do we have here? So we have here a short KOH edge to form these cavities, but they're pretty shallow into a substrate. Then I do a deposition of epitaxially grown silicon, which is in situ P++ doped, so boron diffusion. I remove this and I grow another layer here. Sorry, I said epitaxially grow silicon. That's not true. This is silicon dioxide. This darker area here. Okay, so I fill here these areas with silicon dioxide with an inverse mask compared to that. And then I remove the middle mask here. I connect these two with the silicon outside. And this can be removed and then glued onto a glass, well, glued on bonded to a glass substrate. And this is a Nordic bonding. You need to have some metallization, gold chrome in this particular case, and this is. Do I have the dimension here somewhere? No, but this forms a very, very small pressure sensor. So side dimensions of this is well below a millimeter. And lastly, about pressure sensors, this is a device from Bremen in Germany. There you see structures like this. There's the actual better view of the structures here in the middle, or here. Right? And the interesting thing here is that you have not one membrane, you have an entire array of membranes. Right? And they are arranged in such a way that the capacitor of one membrane is in parallel to the capacitor of the other membrane. Well, they're all in parallel, and capacitors in parallel, they add up. So in this way, they make an array of membrane, capacitive membrane, and they are adding up, so giving you more capacitors. So it's just another example. So this is a surface micromachine capacitor, pressure sensor. Okay. So these were capacitive pressure sensors. I come back to capacitive transduction. Yeah? But what I want to do now, the following slides, is introduce you to another transduction principle, which is actually piezoelectric transduction. So they have piezoresistive, they have capacitors, I'll come back to, and we have piezoelectric. And these are the three most important transduction mechanisms for MEMS device. You can argue there's also optical transduction. You can use tunneling effects for transduction. Yes, you can do all these sort of things, but this is not mainstream. So, piezoelectric it's actually increasingly becoming important in MEMS technology, for ultrasound applications, for example. So let's go through this very briefly. So, piezoelectric effect, well, came from the Curie family. Yeah? It's a reversible effect. So a mechanical stress leads to a net polarization in some materials, electrical polarization, and that you can measure, so it basically creates a charge. Right? And you can also do the other way around. If you have a lighter, not the one with the little wheels on, but the one that you click, a lighter that you have to click to light up the fire in the chimney maybe. Then you can also apply, sorry, this of course this, but if you do it the opposite, if you apply a voltage, you can also create a mechanical strain or stress if you are in a material that is in a linear range. So it's a two-directional effect. Right? It allows me to go from the mechanical domain into the electrical domain, but it also allows me to go from the electrical domain into the mechanical domain. So I can use this for sensing, and I can use this for actuation as well. Right? Now, can I do this with capacitive sensing as well? Any? No?
No.
No?
No. No.
Can I do it with piezo-resistive transduction? You can't do it very well, let's put it this way. Now with electric, with capacitive transduction, you say no, I don't agree with that. Why? Okay, let's make a small detour. So capacitive, we have one electrode that is movable, and the other electrode is fixed. So that was our sensing principle, right? And you're saying I can't do it the other way around. Well, I can do this now. I can put here a voltage. Right? Across my two electrodes. And a voltage creates an electrostatic force, no? And you know this equation, no? So the electrostatic force is, well, epsilon A times the voltage squared divided by the gap here. And the gap, like before, is D minus X divided by the gap squared. Right? Electrostatic force, you've seen that, no? Why? Well, you have, it's Coulomb's law at the end of the day. You have charges here, you have charges there. Or they create a force. And if this is movable here, so you draw this a little bit, so this is it's a plate. Okay, and here we have a little beam. Alright, this beam is allowing my plate here to flap up and down, let's say. Right? So if I now change the voltage here from, well, we start with 0. I crank it up a little bit. I create an electrostatic force. It's V squared divided by the gap squared. Right? So this voltage, this force, which is voltage, is always attractive. It's a squared quantity divided by another squared quantity. Epsilon A is of course positive. So this will start to move down. If I stay with this example, it will somehow bend down. Right? They will get attracted to my bottom electron. So, I'll come back to this again. Capacitive transduction is also capable of going either way, from the electrical to the mechanical, and from the mechanical into the electrical domain. Because it allows me to create an electrostatic force. What you cannot do is make this push away, because your electrostatic force due to the squared law relationship is always positive. Okay. Okay. But I wanted to talk about piezoelectric sensing and the piezoelectric effect. So, piezoelectric effect goes from mechanical domain to the electrical domain, and from the electrical domain form of voltage to the mechanical domain. Yeah? So here you have a piezoelectric material. You put a force on there. You push. This is your lighter, and you create charge. What is written here is you create a change in charge in response to a change in the voltage. So that means if the table was a piezoelectric material, if I push on it, it's the change in the force that creates a electric charge. If I push and keep on pushing, but I don't change my force, it will not create a electric charge, an electric signal. And this is one of the important limitations of piezoelectric sensing as well as actuation. It goes in either direction. You always have to have a time varying signal. So the sensing as well as the actuation is only suitable for signals that vary in time. Now you can come along and say, yeah, but hang on a sec, everything changes with time, nothing is constant. Even the universe is not constant. It has been Big Bang 14 billion years ago, whatever. So the longest DC component you have is 14 billion. Yeah, okay. What I mean with this is that there's some sort of lower frequency where this doesn't work anymore. And in a practical, in any practical sensor, the change or the frequency at which the signal changes has to be above a certain threshold. And again, I'm giving you sort of rules of thumb today. So it's difficult to make piezoelectric sensors below a few hertz response. So below 10 hertz or so, piezoelectric sensing is not a good choice. So that's the reason I didn't show you any piezoelectric pressure sensors. Maybe for the guys wanting to measure pressure in a turbine, that would work. But for barometric sensing, where things are changing with time constants of maybe an hour or so, piezoelectric sensing is not a good idea, because the change is rather slow. I ask you in the exam, would you consider piezoelectric sensing for a normal pressure sensor? And you say yes, then you're in trouble. Okay? So piezoelectric sensing has a lower cutoff frequency. Okay, so how does it work? Well, we have here a relationship between the charge, or the change in charge, with the change in the force. And then you have here some sort of probability constant. Yeah? And this constant here called dij. So what does that mean? Well, it points into a similar direction as the story of the piezoresistive sensing. Piezoresistive, it was somehow in silicon highly related to the crystal orientation. And for piezoelectric, it's a similar story. It's also dependent on the crystal orientation. And I'm not going to go into this in detail. Now, silicon itself, pure silicon, is practically not piezoelectric. Silicon dioxide, glass, in a form of quartz, is piezoelectric. Right? And this has then an implication on the crystal orientation, and the silicon dioxide crystal is again different to the silicon, so I'm not going to go there, but just keep this in mind that the direction plays a role in this coefficient. Usually what you use for piezoelectricity is the D33 coefficient, because that tends to be the highest. So if you turn this in a certain direction, D33, that's the highest. Now if I have a change in charge, I also will have a change in voltage. If I divide this by capacitance, and well, I can put this equation in there, of course. And my capacitance, this is here in the denominator, so I have epsilon A and the T here. And basically, why do I have a capacitor? Well, piezoelectric material is a dielectric usually. Quartz is a dielectric, is a glass. And you put a conducting plate at the top and the bottom. And now you push, and because it's two electrodes, you have also a capacitor with a dielectric in between, like quartz, for example, or some other ceramics. So here it's not the effect that one electrode moves with respect to the other, displacement, like with the capacitive sensing. Here it's due to the piezoelectric material that we get a change in the voltage on the capacitive plates. Now, what's going on in the material itself? Okay, so here I've got silicon is not piezoelectric. Why? It has a cubic structure with a center of symmetry, and it has covalent and not ionic bonds. So this is the background of the material science. So crystals with a central symmetry usually don't have a piezoelectric effect, because, well, what does it mean? If I do a 2D representation, so this is my polarization, Pi, and if I sum over all the Pi vectors, right, they come out as 0. So all these arrows here, if you have a nice symmetric structure, so this is symmetric, and I push on the material, then okay, so these lines, these arrows get smaller, and they get a little bit longer, but if I sum over all the vectors, I still get 0, right? So that's, in a nutshell, what you have in silicon. So you have a center of symmetry, right? And the polarization, regardless whether you have external applied stress, that shifts the atoms in their crystal slightly, makes this distance a little bit smaller and this one a little bit larger. Nevertheless, if you sum over all these vectors, you get a 0. Now, the piezoelectric material is a crystal that does not have a simple center of symmetry, and it's something like visualized like here. Yeah? So if you have a structure like that, so you have here, if you look at this atom there, you have these 3 vectors to sum over, and if this is in this state, then again the polarization vectors come out as 0. But if I if I now squash here again, then they still come out. If I squash now here, you see that these 2 guys get a little bit shorter, and this one gets a little bit longer, right? So if I now sum over these 3 vector components, then I get a polarization vector that is not 0 anymore, and therefore I get a charge. Now, which direction this effect is now the biggest is not so obvious to see. But, this is where this crystal orientation in the crystal planes play a role now. It turns out that this direction here, along this vector here, that's the most sensitive direction, and this is this D33 direction. So another way of visualizing this, or if you just take one of these 6 corner, there's 6 corner construction here, like here. So if I squash this now, material with a crystal orientation like here, I squash this now, I get an output voltage. Because you create a net polarization that is different from summing it up. It doesn't sum up to 0 anymore. Okay, so this is a bit of a hand-wavy explanation. I'm aware of this, but otherwise I have to spend a full lecture on going into crystal orientation and like piezoresistive notation and so on. So we'll leave it at that. I think it's sort of visualizing it reasonably intuitively. Yeah? Okay. Here is a table. Different materials. Quartz I mentioned already. So this proportionality constant D33 relates charge to force C over N. It's multiplied here by 10 to the minus 12. Right? And quartz has something like 2.3. There's a bunch of other materials that have, as you see here, much higher piezoelectric coefficients. So these materials, if you want to use it for sensing, they give a much better or stronger piezoelectric effect compared to simple silicon dioxide quartz. There are a couple of other parameters given here, but they're not so important. So if you look at some other materials, PZT, this is a lead compound ceramic, right? That has 370. So this is the highest in the list. And no free lunch again. There's lead in it, and lead is not very healthy. So that's well, it can be a problem. It doesn't have to be a problem. The zinc oxide is a good substitute, fairly high, D33. Right? Zinc oxide is pretty harmless, so you can put this, you can swallow this. Nothing will happen to you. Swallow PZT in a pill or whatever that goes through your guts and does some sensing or actuation, and it's not so healthy. You don't want to do this too often. And here are some other ceramics, and here's also this PVDF is a poly, a poly meaning a chain of some organic compounds. So that also has a, well, it hasn't got such a strong D33, but it's a polymer and it's very easy to work with. You can actually spin coat it on like a photoresist. What is also important is whether there's a thin film form. So often what you want to do is you want to deposit a thin film of this piezoelectric between two electrodes. That's difficult with quartz. This is good with PZT and selenol, zinc oxide. You can sputter this, or you use what's called a salt gel process. These are ceramics here. No? Okay. So a bunch of materials, depending on the application that you want to do with it. Now, how do I? Yeah, go on.
And we said at the beginning that piezoelectric crystal they don't work at DC.
Yeah.
But if we go to the when you show them,
yeah. Good question. Yeah. So why do they only work at DC?
I mean, you've shown us if you swatch it, then you have.
So the polarization stays, right? Actually, let me go to the next slide. I'll explain it. So how do I measure? How do I measure this change in charge? Right. So I can do this. So this is an op amp, standard op amp, and I have not what you maybe are used to resistive feedback. You have a capacitive feedback. So this is sometimes called a charge amplifier. Amplifies a charge. Now what you said is very good point. So the polarization remains, but there is no known way of retaining charge on a real substrate, because you always have a DC path to ground, a parasitic DC path to ground. You don't agree? No? So, especially in a small MEMS sensor, right? You will have always these parasitic components, and that means over time your charge will leak away. Right? So it's a practical reason. If you could perfectly isolate your piezo crystal, right? You push on it, create a charge, and it has absolutely no way to leak away, it will remain there. And then you can push this lower frequency boundary to lower frequencies. But in any practical implementation, you will always have a leakage path to ground. Right? So that's the reason why you have this lower limit there. Okay. So what is this here? Any idea? Why you need that?
To increase.
Sorry? the right direction, but a little bit more. Yeah.
It's an integrator.
Hmm? Well, it's an integrator, yes, but without the R, it's an integrator. So independent of whether it's a piezoelectric material or sensor, right?
Oh, okay. That's for the charge.
What happens? So I make this one puff. I have an inverting amplifier. And you said it's an integrator, yeah? So we do electronics engineering now, okay? So it's an integrator, yes. So I'll put a sine wave in there, and out should come a sine wave again, eh? A cosine wave or whatever, yeah. Right? It's got a gain of 1 somehow, or let's make it a gain of 2. Yeah. So. Okay? So if you build this in the lab, does this work? I'm talking about not a MEMS capacitors anymore. I'm talking about an ordinary 2 capacitors. What happens? This is what I want, and this is what I get. How does what I get look like?
There's no DC, there's no bias.
Yeah, and this flat line.
And the DC is infinitely amplified.
Yes. So you have no DC gain. Your DC gain is infinity. So what happens is actually it shoots into saturation, either positive or probably negative because it's an inverting amplifier. Okay. So an ideal integrator or purely capacitive feedback, you will always saturate your circuit. Even if you do this in SPICE, it will complain. Yeah. So this is the reason for this resistor here. You always have to have a resistive path that sets the whoever set this the DC gain to a sensible level, right? Okay. Or I can. It's even independent of what kind of element I have here. Even if I put a resistor here. Okay. I'll put a resistor here. Actually, if I put a resistor here, I don't have this. Then it becomes a real integrator. Okay. That's a real integrator. If I do this without that, I also will immediately saturate, because the DC gain is whatever the open loop gain is of your op amp, right? So capacitive feedback around an op amp, purely capacitive feedback around an op amp, always is effectively giving you a saturation. So that's the reason why this weakly R is. You can make this large, this R, to approximate your ideal integrator or charge amplifier. You can make this, I don't know, a giga ohm or so. 10 mega ohm, whatever. Okay, yeah, I mentioned this PVDF. So this is this polymer. If it's in its natural form, so it forms this sort of change of H carbon and hydrogen and fluor atoms, and this is repeated n times, so it forms a polymer chain. But this polymer chain is kind of unordered, right? And it has no orientation. What I can do with it, if I put this in a high electric field, right, then the chain becomes orderly. It becomes like this. So you have the fluorine or the fluor atoms on one side and the hydrogen on the other side. So this polarization induces this orderly structure, and if I take this away, it's going to remain in that, and this is what creates the piezoelectric effect then, right? Or the piezoelectric material property. Okay, so as I said, it's going to be a very short side tour into piezoelectricity. I'm not going to talk too much about it. Yeah? So sensors, dynamic measurements only. Charge always leaks off. Huh? So that was your question here on the slide. And the lower bandwidth, yeah. Again, it depends on the sensor. So it depends what kind of sensor it is. It depends on your design again. It depends on what you specifically how well you isolate this from the outside world. But as a rule of thumb, below 10 Hertz, it becomes difficult. Yeah, and then we talked about actuation here as well. That's if I apply a voltage, I get a mechanical displacement. Okay, I think yeah, I want to talk about microphones a bit more, but I think we'll leave this for today. So maybe regarding the presentations, everything clear? Everybody got a paper and got a group, and you know where and when to go. Yeah. Okay, have a good weekend.